The most important question after the Broglie wave was formally established, that what kind of equation the particle should follow. So our timeline was like this. Particle as wave. No, initially it was waves as particle. That is like photoelectric Compton, black body, particle as wave, the Broglie. Then the question was, what is the equation the Broglie wave follows? This was answered by Schrodinger. The Schrodinger equation. We won't derive that equation because Schrodinger initially argued something from wave-particle duality, something from classical physics, etc. In some books, there are kind of a derivation type of things, but we won't do. We take this as a fundamental postulate, Schrodinger equation, that any particle should follow this equation. This is our main equation. In one dimension, there's a very strange thing called psi. Don't worry about it. If it could be a function of x, could be a function of t, in most general form, psi is itself a function of x and t. Psi is a function of x and t. That is, to be sure, this is one dimension. More general form is h psi is I h del psi del t. H is the Hamiltonian. If you don't know what a Hamiltonian is, don't worry. You will learn. For the time being, let's take Hamiltonian in generally represents the total energy of the system. Okay, so if Hamiltonian is the total energy, where is that energy here? It is the most important question. I will answer it one by one. First of all, this equation looks very strange. First question will be, what is your psi? I will answer. Second question is this derivable? No. Where from you get the equation? The answer of this question is, it is a postulate, just like a Newton's law of gravity or Coulomb's law. We don't know how to derive them. We take them as fundamental postulates. So it is a law of nature. We can question that why this should be the law, but we accept the laws. We accept at the very fundamental level that we cannot explain this in terms of other fundamental law. So for the time being, it is a fundamental postulate. Law of nature. What is psi? Next slide. But all quantum mechanics will be revolving around this equation. V is the potential, del square psi del f square is the space double derivative. I mean, you can see this is double derivative with respect to x of that psi. Some unknown quantity psi is there. If you are taking double derivative of that psi multiplied by your minus h bar square, I think you know that h is a Planck's constant, multiplying by h bar square by 2m, double derivative of your psi, add v your potential multiplied by your psi, that should be equals to I h bar. How I comes, we'll discuss, don't worry. I is that the same I, that is from square root of minus 1, that you are familiar in the complex square number, that I h bar del psi del t, double derivative with respect to time of that psi. So what is psi? That's the main question. So the psi actually means the probability density, that is the Born approximation, Born interpretation of psi. So it's very to be stated very clearly that psi star, in one dimension we're dealing with psi star psi. If we integrate it from say x1 to x2, it gives you the probability to find the particle between x1 to x2 at time t. Psi star psi integration dx from x1 to x2, that means probability to find the particle between x1 to x2 at time t. So if you have a picture or image, so it would be like this, that if you have a psi, you take its mod square, so that psi star psi is actually, that is mod psi. This is this. So if I plot psi star psi in a graph, and say this is x1 and x2, and this means it's a and b, so the integration, the area between that a and b, this much will give you the probability to find the particle between a and b. So this area, so this green shaded area, this area is the probability. To find the particle, I'm writing the same thing again and again, between A and B. So if we take this, this is also an assumption. No, this is not a particular assumption. Our fundamental postulate of Schrodinger equation includes this interpretation. that. So the whole postulate will be a particle or anything, a particle or a wave or anything, whatever. So because we don't have this distinction between wave and particle right now. So, but right now we'll be dealing with a particle, so-called particle which have a mass. So some particle which have a mass m in one dimension follows this equation. This is the Broglie wave equation, with psi is to be defined as psi star psi dx integration will give you the probability. So the definition of psi is this, and that psi follows this equation. That is overall the main postulate of Schrodinger equation. So, and this fundamental postulate give you many properties of psi. Just from this definition, I can have other properties. I will deduce. These properties are not postulate. If this is the postulate, then the properties are to be deduced from here. If psi star psi is the probability, then integration of all space psi dx should be 1, as the total probability to finding a particle. The particle, if the particle exists, it has to be somewhere. It has to be somewhere if this exists. Probability is to be 1. Okay. Next thing will be this is called as normalization. Psi has to be 0 as x increases to infinity. Psi should not have any finite values at infinity. Otherwise, this will not be satisfied. Imagine that the psi star psi this continues and goes to leads to some value at infinity. So if you integrate it, this will diverge to. You can have an example with that psi is going to have some finite value at infinity, and surely you can think that then integration, the area bounded under that curve, will also goes to infinity to get the integration finite. So if you have any psi, the psi has to be, psi may be here and there, whatever the psi behaves, psi has to go to 0 as x increases. If your psi is having some finite value, or something vibrating but having some finite value, if this goes on and goes on, this diverges. Area diverges. Is my reporting is on? Okay, yes. So this has to be 0 as this increases. Has to be 0. Just a second. The next thing is psi should be continuous always, because if psi is not continuous, that means if at a point we are not getting the psi properly, that what is psi, then the probability will be undefined. That cannot happen. I will write a diagram. Don't worry. Psi should be continuous everywhere. So friends, that was the preview, like partially cutted video. So if you like that video, if you like the way I teach, just to search physics guide in Google. You should get this physicsguide.in at the top or at very near by. So this is my website, physicsguide.in. So if you're unable to view, so this is physicsguide.in. So you go to physicsguide.in, or you can directly go to physicsguide.in there. So here you see the courses. You directly go to the courses, or here you do the browse courses. Here you see we have started this course, this quantum mechanics 1. Don't go to the other courses. This course I just this was a free course, but I couldn't complete it. This course has not been started, and this is a very specialized course for CU students, so forget about it. The first you see that quantum mechanics 1. So this course you can buy it. The price is just $9.99. You just add to cart. They will ask you for sign in. It will just work for net. It will just work as Netflix works, as Amazon Prime works. You'll create a, you'll register, you'll create a email and password, you'll create an account, then you will add it, then you will add to cart, you will make a payment, then your account will get activated and you'll be able to access the course. Thank you. Please do consider subscribing to that course.